kidding. So for all of you out in video land, you're going to need the special graph paper for graphing trig functions in order to do this assignment. So, we get to learn some new terminology. Okay. When you graph trig functions, they are what we call periodic. Okay, if something periodically happens, what's that mean? Yeah, maybe something periodically, something happens every 2 or 3 days. Periodically means though it repeats itself. The same thing happens again, you wait a while, same thing happens again, you wait a while, the same thing happens again. So in other words, the graphs of trig functions repeat themselves over and over. So if you know how to draw the one basic, what we call cycle of it, then it just repeats itself continually after that. So that's kind of the good news. Once you learn how to make the basic shape of it, you know it just is going to repeat over and over. And our big thing is going to be today, how do I figure out what the graphs of sine and cosine look like? That's what we were doing. And to get the graphs of sine and cosine, we are going to plot some good old points by hand. But before I can, there's going to be more stuff here on this screen in a moment, but we have to get the graph drawn, then we'll come back to this. So I need to get some graph paper. Okay. So, what did you notice about your graph paper and how the x-axis is labeled? It's labeled in radians. Imagine that. Okay, but why are these points placed so weirdly? They're not evenly spaced. Why is pi over 4 and pi over 3 so close together, but then pi over 2 farther away? Why on earth is it getting this? Well, let me ask you to notice something. How many boxes out is pi? It's 1, 2, 3, 4, 5, 6, and actually it's more like about a quarter. And to be exact, it's at 6.28. So what's 6.28?
2 times pi.
That is 2 times pi. 2 times 3.14. They're actually placing pi at 3.14. It means the boxes on this graph paper are half. Every box on this graph paper is a half.
What?
So they are placing pi at exactly 3.14. So they're numerically placing these correctly. So consequently, why is there a dotted line up 2 boxes up and 2 boxes down? That would be 1 unit. That would indeed be 1 and negative 1. Did you just have to draw me something on your test that related to 1 and negative 1?
Oh, this is that big graph thing.
Yeah, that graph thing, and the graphs of sine and cosine, or sine and cosine's values were where? In between 1 and negative 1. So when we graph it, they're going to be between 1 and negative 1. So because the one, in fact, all 6 trig functions, like the secant and cosecant, were outside 1 and negative 1, that will apply here too. Tangent, cotangent could be everywhere. So do remember when you're graphing on this paper then, as you go up particularly up the y-axis, every 2 boxes is a unit. Now, on those answers I gave you that are photocopied from the answer key of the book, I think when they mark tick marks on their axis, it's 1 unit. Every tick mark is a unit. It's not built like this graph paper. So that's important to understand that. Okay. What angles do you notice are on this graph paper? Got pi over 4, pi over 3, pi over 2. Are those angles you've seen somewhere before?
Yeah,
on the chart. It's graphing the special angles on here. But where are the 6s? Luke, put the book away.
maybe that's on the
The 6's are on here. They're marked.
Those are the little lines.
Yeah. See the little tick marks that are unlabeled? They didn't have the space. But pi over 6 would be, pi divided by 6 would be the smallest. So that first tick, unlabeled tick mark, that's pi over 6. Okay. So can anybody figure out what this next one is out here right before pi? 5 pi over 6. Okay, because the others, 2 6 is really a third. 3 6 is a half. 4 6 is 2/3. So you don't hit another 6 that doesn't simplify until you get to 5 6. Pi is 6 6. So that one after it, yes, is 7 6. 8 6, 9 6, and 10 6 all reduced. So that one right out there before 2 pi is 11 6. Yeah. And then 2 pi would be 12 6. Yeah. And then, of course, it's the same when you go on the negative side, too. So the 6's are on there. All the special angles are on there, if you need them. All right. We have to do this the first time. Then we'll discover the quick and easy way once you see the pattern. But the first time, we have to actually plot this thing by good old basic t-table. And since they've got all the special angles on there already for us, wouldn't it be smart to just graph the special angles table? Yeah. So we're just going to graph the special angle table, which of course we all know the order of those points. 0, 6, 4, 3, 2. All right, what's the sign column?
0, half, square root 2 over 2, square root 2 over 2.
1. Okay, and just for your benefit, square root of 2 over 2 is about 0.7. Square root of 3 over 2, decimal is about 0.86, so we got a rough idea where to plot these babies. So if I plot those points, I have 0, 0. Pi over 6 over has got to be a half up, which would be where on this graph paper?
The one line above it.
Yeah, half would be exactly one box up. Pi over 4 over is supposed to be 0.7 up, so you're going to kind of have to guesstimate it in between the first and second box. 0.86 is getting a little higher when we get to pi over 3, and then when I get to pi over 2, it's up to 1. So golly gee, what's it made? It's a curve. Okay, now that can't be the whole graph. You wish, but no, it's not. Okay, so if we do it again, if I do it again, I'm going to hit 2/3, 3/4, 5 6. That's got a 3 on the bottom, so won't it be the same value?
Yep.
It will. 2 pi over 3 will be the same thing as pi over 3, so it'll be back to 0.86. 3/4 will be back to 0.7. It is going to be a hill. You are correct. Okay, why do you say it's a wave?
It's going to go back up again.
Well, okay, got to think about this. Thinking on the clock here and thinking quadrants. We just graphed pi over 2 to pi. Pi over 2 to pi on the clock is the second quadrant. Sign was still positive. When I start to go to 7 pi over 6 on the clock, I'm in the third quadrant, which means what do I know about sign?
Negative.
It's negative. So in the third quadrant, you're going to do these same numbers, but it's got to go negative. So at 7 pi over 6, we're down at negative 1/2. Yes, it's like a huge wave. 5 pi over 4, it's going to be down at 0.7, down at 0.86, and then down at negative 1.
You can't go way up above, too, right? Because it's going to be two constants in a row.
Okay, when I'm in these last coordinates we've got there are the fourth quadrant angles. In the fourth quadrant, sign is still negative. So it's going to do these exact same coordinates and go right back up to 0. So 5/3, a third is still a 0.86. A fourth is still a 0.7. Pi over 6 is a half, and then I'm back to 0. So you've got a lovely wave. Why the numbers or why it's negative? Look at the clock.
What's that one that's on the origin?
2 pi?
The origin.
It says that the numbers, yeah, 3 pi over 2 when it's down. Yeah, that's 3 pi over 2. It's the exact ones you have marked off on your graph paper. It's the same ones on your graph paper. I'm plotting every point you have labeled on your graph paper. And I'm just plotting these exact same numbers every time. So it made a nice wave. If I let it keep going, if I could extend my graph paper farther, what would happen?
Go up and down and up.
Because once I'm past 2 pi on the clock, what am I doing?
Going in.
On the clock, going around.
You're restarting.
This was 0. I graphed from 0 to pi over 2 was the first part of the wave going up. From pi over 2 to pi, that was that part of the wave coming back down to 0. I'm graphing by quadrants. I'm going around here. So if this is 2 pi, I ended at 2 pi. If I keep going to the next angle past 2 pi, yeah, I've already been around the circle once,
Pi over 2.
but then I'm going to go back. There would be a sixth again, then a fourth, then a third. It's going to be like I'm going back into the first quadrant. So it's going to be this exact same starting wave that we came up with. Yeah, it waves this wave forever. This exact wave just continues forever and ever and ever.
Never, never. Sign was positive on the second part.
Sign is that positive. Pi over 2 to pi, it's above the axis. That's positive. Not coming down, but it's a positive y-coordinate. So if it's above the axis, it's positive. If it's below the axis, it's negative. So it was positive in the first 2 quadrants and negative in the second 2 quadrants. Now, you are not going to plot all those points. What are the only points we really need to graph this thing?
Origin, maybe 1.
We need, so we need where it hits the axis.
And then the highest.
Yeah, you need the peaks and the valleys. So when you graph a sine wave, now that you know what it does, you're going to graph 5 points. We are not going to graph all those points. That'd be insane to do that every time.
Thank you.
You're going to graph 5 points. In fact, now you're going to take this thing for me. Since I'm out of room going right on my graph paper, we can extend it to the left. Tell me what this graph would do. It's going to go down. Okay, we want the next valley because it's going to go down. At what number will that valley be? Negative pi over 2. Notice the points you just marked off, 0. Pi over 2, pi, 3 pi over 2, 2 pi. It's the quadrant line. So you're plotting it at the quadrant line. So all I have to do is find the quadrant lines. Pi over 2 is going to be down. What's the next quadrant line? Pi, which is going to be where? On the line, back to 0. 3 pi over 2's got to be up at the peak. 2 pi's got to be back on the axis. So you can create a wave. Okay. The only thing I request is that your waves are curved. Don't, I get this. If these are your points, joint, joint. They are not little pointed mountains. That is wrong, wrong, wrong. I will take off points if you draw me little pointed mountains. Curve them. Yeah, hills. There you go. Make hills. That's good. All right, this is a good place to make it stop for the moment.